So as I said again, the null hypothesis is the same, this is all fixed effects model, the null hypothesis is same, the alternate hypothesis is at least not 1 equals to 0, and the model we are going to have is mu plus tau I plus beta j is the model we are going to have, right. Remember our ANOVA model is the same, it is now we have added. So y is a combination is mu plus tau I plus beta j plus noise epsilon ij. So in the what I call in the ANOVA part I have added one more term beta j in the ANOVA model, okay. So that is my model of the, that is the way I believe that the output is generated, okay. I am not going to model noise, but I am assuming this is the way the output is composed of, it is a linear combination of a constant term plus tau I plus beta j plus epsilon ij. The way I define model, two constraints come into picture, summation tau I should be equal to 0 and summation beta j should also be equals to 0, because the way I have defined the model itself is mean plus variations, and obviously mean is the center point. So the variations around it, the overall variations around it should be equal to 0, so that it mean comes out. So summation tau I equal to 0 and summation beta j equals to 0, and I am assuming, what will we assume about noise is the same, epsilon ij is a IID 0 mean sigma square normal, okay. So epsilon ij is normal 0 comma sigma square, make sense everybody. So mu I, and we have this can be written as what, this can be written as y equals to mu I plus beta j plus epsilon ij, where mu I equals to mu plus tau I, like whatever we did in ANOVA, the same idea, mu I can be written. Now we have a blocking term beta sitting there extra. So said mu equals to mu plus tau I and summation beta j equals to 0. Now we have again a identity similar to that of the what we did in ANOVA. In ANOVA we actually showed two terms for the sum square total. Sum square total is nothing but sum square treatment plus sum squared error, they are orthogonal to each other, right. They will have to be orthogonal because the cross terms go to 0, that is why you have the basic thing. So here there are three again three entities, it is sum square treatment plus sum square block plus sum squared error, and remember all of them are orthogonal to each other, that is why you are able to separate, all cross terms go to 0, because the idea is the error and treatment should have no impact, treatment and error is a noise typically, okay. So it should not contain treatment effects, that is where they are orthogonal, and similarly blocks and treatments are unrelated, because then you would have included in the treatment, block is an unrelated variable. So block and treatment should be uncorrelated, and block and noise should also be uncorrelated, because if it is block is not a specific variable, but if it is random then it will be already part of a noise. So if you are targeting a specific variable, then block and noise should be uncorrelated. So all three are uncorrelated, and you have sum square total is sum square treatment plus noise plus error plus block, okay. So that is the identity we have, okay. So this is, if you look at the each terms, so yij minus the y minus mu the whole square, if you want to call it, that is the overall variance. What is y bar dot dot is nothing but my n mu, y bar dot dot y bar dot dot is mu, sorry y bar, right, y bar dot dot is my mu, right, y dot dot is n mu, capital N mu, where capital N is the total number of data points, okay. So y bar dot dot is mu, so the total variability is what, y minus mu the whole square, that is nothing but, if I want to write it term wise, yij minus mu the whole square. What is the estimate of mu? Y bar dot dot. So yij minus y bar dot dot the whole square is what my total variation along both the axes. I sum it up, that is the total sum squared variation. Sum square total is this quantity which is along both the axes. This is similar to what we did in your ANOVA also. You would have done summation along rows and columns, that is what I am doing. Now that effect I am dividing into 3 parts. One is the what I call the treatment effect, yi dot minus y bar dot dot, which is this is the treatment effect minus the overall mu, the whole square. Okay, that is my variation due to treatment variance, and this treatment variance multiplied for each along summated along each row, summated along the rows is nothing but my sum square treatment. Okay, so I am summing it along for all treatment levels, that is A levels for all columns, B times multiplied with B columns. So this is what I have, sum square treatment. And sum square block, earlier we would not have had sum square block, now we have a sum square block term. Okay, and now you can understand, now by the way I am defining, the sum squared error will be lower than ANOVA if we have to apply ANOVA here. You understand, if you would have not applied RCBD and if you would have just did ANOVA, what would have happened? The second term would have also merged into the third term. So your sum squared error will shoot up. Okay, and therefore you disproving your null hypothesis would be very difficult. Okay, so that is why the second term is there. The second term is the sum square block. So the sum square block is summation along all the columns y dot whatever y dot j bar minus y bar dot dot, the whole square. This is the variation due to in blocking the column wise, and multiplied for all rows will give you the total sum square block. And what is sum squared error is yij minus y dot j bar minus y dot I bar plus y dot dot the whole square. This is the overall, after removing all the blocking effect as well as the treatment effect, this is your sum squared error. Okay, this identity can be derived, I have not derived here. Okay, this identity can be derived just like how you derived in ANOVA, you can derive the same identity here. So this is your sum squared error term. So now the total treatment is sum square treatment equals to, so total equals to treatment plus block plus error. Okay. Now just like we did in ANOVA, we will have to look at the degrees of freedom and then the mean squared error, mean square treatment and mean squared block. Once I know that, then I can take the appropriate F test. You understand, it is a direct extension, okay. So of ANOVA. So what are the total degrees of freedom? The total degrees of freedom is what? What is the total degrees of freedom? A times B, that we can call it as capital N or whatever. AB minus 1 is the total degrees of freedom. And what is the treatment degrees of freedom? A minus 1. What is the blocks degrees of freedom? B minus 1. So now the error you have to calculate, because this is the error term will be AB minus 1 minus A minus 1 into B minus 1. That is your error degrees of freedom, which turns out to be A minus 1 into B minus 1. Okay. So that is your sum squared error degrees of freedom. The degrees of freedom should match both the left and the total should match with the individual, with the summation of the individuals. The total degrees of freedom is AB minus 1, because you estimate a grand mean. So you have AB minus 1 is the sum square total degrees of freedom, sum square treatment is A minus 1, sum square block is B minus 1, and noise, if you sum squared error, if you add up it should come to the sum squared error, right. So that is what we do it. Okay. So then we have mean square treatments. Mean square treatment is sum square treatment by A minus 1, blocks is B minus 1, error is A minus 1 divided by A minus 1 into B minus 1. just like ANOVA. Okay, so far so good. This is your sum squared, mean squared and treatment mean squared blocks and mean squared error. Okay. Now if you want to, the next step, I am again not deriving here, I am just going to show you whatever we have done in ANOVA, it will translate to RCBD as well. So what we have done in ANOVA is expectation of mean square treatment, we derived it, it is sigma squared plus summation tau I squared. Okay, if you remember ANOVA, this is sigma squared plus summation tau I squared. Similarly, mean squared block will be sigma squared plus summation beta j squared. Okay, tau I is for treatment, beta j is for blocks. So your mean square block will be expectation of mean square. Remember, all of them is a random variable, because you are only estimating, you are only estimating using mu grand mu using y bar dot dot, your treatment mean using yi dot bar, your block mean using y bar dot j, etc. Okay, so these are all random variables, so you can take an expectation operator on it. So if you take an expectation operator, this is what I have. So expectation of mean square treatment is what I have, mean square treatment, what is b times summation I equals to 1 to a yi dot bar minus y bar dot dot the whole square. This is what you should be divided by a minus 1. This is what you should be taking. Okay. Now you can expand this, you can take a minus b the whole square, you can ask her to wash her face and come. Okay. You can expand it and then take a summation a squared plus b squared minus 2ab term, okay, and then like what we did in ANOVA, we could the cross terms will get cancelled and you will get the same idea. Okay. Similarly, you can take expectation of a times summation I equals to 1 to b y bar dot j minus y bar dot dot the whole square, that is your mean square divided by b minus 1. Okay, you will end up having this term. Okay. Now expectation of mean squared error, like in ANOVA it is sigma squared. Now you can think of doing F test, and again F test is going to be for what? F test is going to be over expectation of mean square treatment divided by expectation of mean squared error. I am only interested in treatment, okay, I am not worried about blocks. So my F test will still remain the same like that of ANOVA, because you want to reduce the MRC. That is the whole idea. Beta is not of interest to me, clearly block is not of interest to me, that variable is not of interest to me, but if I do not remove that variable or block the effect of that variable, your mean square error will go high. If your denominator goes high, what will happen? You will not be able to disprove the null hypothesis, even though it is wrong. Basically your power of the test will go down. If you do not do blocking, your power of the test will go down. What is power of the test? So your type 2 error will go up, because you are not able to reject the null hypothesis even though it is wrong, because your mean square error has gone high. So now remember, if you do not do ANOVA, mean square error is nothing but mean square error whatever we have plus mean square block.
Can we also do ratio of treatment by block, whether treatment has more effect of the nuisance factor?
Why do I want to? I can do it, but why do I want to?
Whether the treatment has more effect or the nuisance factor is more.
The unrelated variable, the nuisance factor. But why am I interested? You can do the ratio, there is no problem, absolutely there is no problem. But what is of interest to me?
But how will you identify every time which is nuisance factor and which is treatment?
Treatment is something of interest which is under your control. Treatment is you have to, when you do an experiment, you should know what is the variable you are controlling. Treatment by definition means what? It is the input which you have under control. If I am treating a disease, what is it, using a drug, what is it you have under control? The drug. the drug dosage or the different kinds of drug, whatever, that is what is treatment. What is nuisance is everything else, what is not in your control. Nuisance is one particular variable factor, a confounding factor which you know for fact that it is going to affect. Noise is every other term. Noise is IID. What is the assumption what we have made in noise is IID normal 0 sigma square. The moment I say IID, it is coming from various different sources, noise. But if I know for a fact that there is a particular variable, so we looked at paired t-test. Remember we looked at paired t-test. A specimen has to go through, same. I have to be able to give it for treat it under homogeneous conditions. Now homogeneous conditions is a requirement. If I do not do experiment under homogeneous conditions, then I will not be able to compare. How do I ensure that if I do it in heterogeneity, what do I do? I have to introduce homogeneity by assuming these are all experiments done under this condition, block 1. These are all done under, so can I compare experiments done on a sports person versus an old age person? No. So sports person, this is the result. Age group 40 to 50, this is the result. 50 to 60, this is the result. Precondition, pre-existing diseases or existing issues like people with hypertension, this is the outcome. People with diabetes mellitus, this is the diabetes 2, this is the result. These are pre-existing conditions, it will influence your output. Can you do something about it? No, that is a classic example of a blocking factor. So now how do I do? If I do it for diabetes mellitus people, I know this group is diabetes mellitus, block 1 diabetes mellitus. Even in diabetes mellitus you can divide it into. So if I say I am testing for age groups 10 to 50 healthy patients with no pre-existing conditions, then also 10 to 50 is not the same. You may want to do a fine detail 10 to 20, 20 to 30, 30 to 40, 40 to 50, because you know that the age group is supposed to influence, right. What you can do in 20s or 30s, you will not be able to do after 40s, definitely not possible. You can ask people, okay. So the moment you touch 40s, the body will starts saying that I am existing. Until then you will not even know body exists, okay. So that is what it is. No, the entire, say that is the idea, the entire block, right, all the effect of block itself is captured in your sum square total. When you split the sum square total, the entire effect of block is captured as sum squared block, and therefore your noise variance is significantly lower. So what is the, so that is why I asked you first question, what is the effect of blocking? If you do not do block, what will happen? That overall effect will go into the residual, will show it as a noise. Rather I have captured that variance as separately. Now I captured the block variance separately, so that my total variance is a split of 3 things: treatment, block, noise. Now noise is and block, if I do not distinguish them, they would have added them and then the total sum squared error would have shooted up. You see what I am saying? It is only, I am only factorizing the variance due to noise, block separately. I am accounting for block variance separately, not piling them into the sum squared error. If I pile them into sum squared error, the sum squared error will shoot up, okay. And if the sum squared error shoots up, your beta will go high, the type 2 error, and your power of the test will go down. That is why you need to do this. Now what is the drawback of this? No free lunch, there is no free lunch theorem. What is the drawback of doing RCBD? What gets affected? Degrees of freedom. What is, look at the degrees of freedom here and look at the degrees of freedom for the treatment, I mean ANOVA, what is the error degrees of freedom? See, the treatment degrees of freedom remains the same, A minus 1. What is the error degrees of freedom? In ANOVA, what is it? A into n minus 1, A into n minus 1. Here A minus 1 into n minus 1. If you want to call similar, put it into ANOVA terms, B is nothing but n in ANOVA. So, this is A minus 1 into n minus 1. The degrees of freedom have obviously dipped. Okay. So, there is always a trade off. Okay. So, your degrees of freedom have gone down compared to that of ANOVA, because now you have separately considering the blocks. Okay. And ratio of block to treatment to block people also do, okay, but it is case specific. Why do I need it? Okay, I am only looking at the effect of treatment, right. So, why do I need it is a question. By very definition of nuisance, I do not have a control over it. That is what the definition of nuisance is.
So
yes,
now
sir.
that we have separated noise and nuisance, once we get the power of the treatment, so for which block it is associated? It is associated for any specific block or altogether?
So, you are saying, can I fine tune the blocks, if I want to put it that way, because there are block itself is multiple levels. Beta is one nuisance variable affecting at multiple levels. That levels is nothing but block levels, like treatment is only one factor at A levels, block is another variable at B levels. Now, you are asking which B is significant compared to which other B. You can all do that using the same old good old t test. Like after you do ANOVA, what did we do? We only know that from ANOVA, what do we know? We know that one particular treatment is different. We do not know what it is. How did we then do it? We started using t test, 2 summation mean squared by n, we started using t test. The same way you can do a hypothesis on blocking itself and then see a ratio of block over noise and then say which block is significant compared to that of noise. If you want to understand about blocking, you can do the same thing what you could have did for treatment, you can do the same thing for block. You understand the same exercise. Now you say tau I equals to 0, you can say all betas are equal to 0, that is blocking is even not required, all betas are equal to 0, then you can do a hypothesis testing and figure out which blocks are important. That is a possibility. Clear? Like what you did for treatment, you can do the same thing for blocks, but remember that is a nuisance variable you do not have control over.
Since the overall course we are very much interested in seeing a distribution, so is there any relation in the distribution of the F test for each of the block, or it remains constant for some normal distribution or something?
See, our assumption about this entire thing is revolves around normality. Epsilon ij is normal 0 comma sigma square. So, every variable tau I, that is why I said tau I, your truth is mu equals to, you have assumed the truth to be what, mu plus tau I plus beta j plus epsilon ij. So, your epsilon ij is normal, your assumption, and therefore your y is normal, and the very moment you are doing F test means what, it is a ratio of 2 chi square, and what is chi square? What is chi square? Summation of squared normal random variables. So, all distributions are assumed to be normal. If you do not have a normality assumption, all this ANOVA F test will fail. If there is a significant deviation from ANOVA, from normality, these things will fail. If time permits, we will see what is known as bootstrapping methods, where you can do away with normality test. Okay, I mean do away with normality assumption, but so far all of them runs around normality, and the reason for assuming normality is central limit theorem. Okay. So, again now we can go back to the linear least squares way of thinking. to estimate the parameters, right. ANOVA we did it, similarly we can extend it to RCBD. Okay. So you have yi dot is summation of along b axis for I equals to 1 to a. So this is yi dot, and y dot j is summation along a for each b, okay, that is y dot j, and y dot dot is the entire summation, the total sum, okay, and you have average of treatment which is yi dot divided by b, average of the blocks y dot j divided by a, and the total average is y dot dot divided by capital N, where this is y dot dot. Capital N equals to a times b, okay. This is the total sum squared identity that we have seen, okay. I have derived it here, okay, I have shown the derivation here. So you can how to split it into two parts, okay. So first I do it into two parts and then expand it, so you will get it idea. This is a minus, so what did I do, yij minus y bar dot dot, what did I add and subtract, what did I add and subtract, this is my yij minus y bar dot dot. How did I get this, by expanding, how can I add and y dot this thing, I should not be able to, I should add and subtract the same quantity, right. How can I add different quantities, actually both are added and subtracted, you try doing this, okay. I have derived, I have shown it here how it is done. So this is the sum square identity, you can demystify this, go through this. So this is my table here, okay, same table like ANOVA except that I have no blocks, okay, a minus 1, b minus 1, a minus 1 into b minus 1, capital N minus 1, treatment by a minus 1, block by b minus 1, error by a minus 1 into b minus 1. My F test is usually on treatments, I can do the same for blocks also, nobody is stopping me, okay. Now I can do the regression way. So far so good, these are the estimates, okay, these are the formula. If you want to just go by ANOVA, these are the formulas to be remembered, but you can derive this also. As I told you, we will be able to derive this. For ANOVA we derived using the regression idea, same way we can derive it here, okay. So this is the formula for sum square treatment total in blocks, and sum square error is always a subtraction of all. Now I can derive it using the regression way. How many equations will I have, how many regression equations, totally how many parameters, remember rules, how many parameters are there, how many parameters are there, y equals to mu plus tau I plus beta j plus epsilon ij, how many parameters are there, mu is 1, tau I is a parameters, beta j is b, so a plus b plus 1 equations, right. For ANOVA it was a plus 1 equations, now this is going to be a plus b plus 1 equations, clear. So that is rule number 1. So the total number of equations is going to be equal to the total number of parameters, which is a plus b plus 1 equations. And what is rule number 2 in regression? I do not want to differentiate and do all of this, right. You could differentiate and do the normal equations, we call it as normal because as I said they are orthogonal equations, the shortest distance is what you find, which is normal. So how do I write the right hand side of the equations, normal equations? The right hand side is the summation of number of times the parameters appear. So now mu appears in all the data points, so summation of all the data points is what, y dot dot, and how many times tau 1 appears, a times, so it is y1 dot which is along the first row alone, and tau 2 appears second row y2 dot, and tau a appears eighth row, so this is ya dot, okay. And similarly for blocks what will happen, y1 y dot 1 y dot 2 up to y dot b. So how many equations are there here? How many equations are there? A plus b plus 1 equations, A treatment equations, B block equations and 1 mu equations. So A plus b plus 1 normal equations, the right hand side you can write. How do I write the left hand side of the equation? The left hand side is nothing but summation of all the parameters, summation of all the parameters multiplied by how many times that particular parameter appears in the equations. So mu hat appears how many times? AB times. Tau 1 hat appears how many times? B times. Tau 2 appears B times, columns B times, and beta 1 hat appears A times, beta 2 appears A times, etc. So this is my first equation. The second equation what will happen? The second equation is an equation governing for tau 1, okay. How many times mu hat will occur for tau 1? Only B times, only number of columns times B times, and tau 1 hat. So remember this is the right hand side. In y1 dot, how many times mu will appear? B times, right, and how many times tau 1 will appear? B times. Tau 2 will it appear in y1 dot? No, tau 2 is second treatment, y1 dot it will not appear, zeros, okay. And how about blocks? So this part is clear. So these treatment, all these treatment coefficients will be multiplied by zeros. Remember the third rule is nothing but summation of all the parameters, all the coefficients pre-multiplied with the terms, the coefficients are nothing but the number of times it appears in the right hand side. The right hand side is first equation is y dot dot, number of times mu hat appears in y dot dot is what? AB times, the total times. Number of times tau 1 dot appears in y dot dot is what? How many times tau 1 dot will appear in right hand side? B times, the total number of columns, right. And similarly tau 2 dot will appear B times, beta 1 dot will appear A times, beta 2 dot will appear A times. So that is why the first equation. Now coming to the second equation, the equation for tau 1, mu 1 tau 1 is nothing but y1 dot. How many times in y1 dot mu will appear? B times. There are B data points, right. For you are taking a first treatment and you are going across, first treatment is what? This row, okay. How many times this will go? B times, okay, B times. So this is what? Y1 dot B times, and B is nothing but your small n in your treatment. So in ANOVA if you think this is nothing but your small n, okay. And then how many times your tau 1 will appear? B times. Tau 2 will it appear in y1 dot? No, it is an equation about treatment 1. So treatment 2 will be 0, treatment 3 will be 0, treatment A will be 0. Now coming to it, blocks, how many times beta 1 will appear? How many times beta 1 will be there in y1 dot? It is along one column, along the entire column. Beta will appear once, beta 2 will appear once, beta 3 will appear once, beta B will appear once, because it is along all the columns. So the columns if you look at beta 1, beta 2, beta 3, all of them will be there. So that is why you have this equation beta 1 to beta B, okay. So remember just to apply the regression rules, okay, otherwise you have to differentiate and derive it, okay, that is going to be even more painful. I told you both the ways, the differentiating and figuring it out are the simple regression ideas, okay. Now this is for tau 1. If you write an equation for beta 1, what will happen? Beta 1 is along the columns, beta 1 is for block 1, okay. How many times it will be there? A times, okay, because your right hand side is what? Y dot 1, your right hand side is y dot 1, which is the first column all rows, okay. First all the rows summed along all the rows, okay. First column you are impacting. So beta 1 will appear, so in this equation, okay, mu will appear A times, okay, because now you are looking along this way, mu will occur. This is exactly opposite of treatment equation. If you look at treatment, it will be B, here it will be A, and your tau i's are going to be added only once, like your betas are added only once, tau i's are going to be added only once, and your betas will be multiplied by A's, like your tau i's are multiplied by B's, okay. There is a pattern here, very clear pattern, okay. So this is just applying rule number 3 of your regression equation. And are all these equations independent? Are all these equations independent? How many equations are independent? How do I get the first one? If I add all these equations, I will get the first equation, alright. If I add all these equations, I will get the first equation. So at least the second through A plus 1 equations sum to the first normal equations, right. So this whole thing if I add, I will get this equation, this entire A plus 1 into this A equations and this B equations, if I add, I will get the first equation. No, that is where there is dependencies, okay. So one obvious dependency is if I sum all the equations, I will get the first equation, okay. And then if I sum only, what else you are saying? This one. So if I sum this alone, what will I have? I will have A times, I will have this one. So this part if I sum, I will get this equation, and this part if I sum, I will get this equation. So there are actually two dependency equations, not one, two dependency equations. If I sum the tau 1 to tau A equations, I will get the first equation. If I sum beta 1 to beta B equation, I will get the first equation. So there are two dependencies. So total equation is A plus B plus 1. I have two dependencies. Now for two dependencies, I have two independent constraints, which is summation tau I equals to 0, summation beta j equals to 0. So that way I have A plus B plus 1 independent equations, parameters, and A plus B plus 1 independent equation including the constraints. That way we will be able to solve it.